Video we are going to see about geometric primitives. Geometric primitives forms the basic building blocks used to describe three-dimensional shape. So in this video we are going to see only the 2D geometric primitives, which are 2D points, 2D lines, and 2D conics. If you are aware of computer graphics, then you might have heard the 2D points, lines, and conics. If not, let us see in detail. So before the slide, let me try to explain what is 2D point. So we know if we are taking a paper and we are keeping a dot, which is known as 2D point. So a 2D point can be represented as a 2D point can be represented as x equal to x comma y, right? We know x comma y, which this point can be 2 comma 3. We usually represent as x comma y. So this belongs to a real space. We are seeing it, we can touch it, we can feel it. So this is a real space. So this can be written as x equal to x comma y, can also be written as matrix form. So x xy. So this is a matrix representation of a 2D point. And this point x comma y, x equal to x comma y, is known as inhomogeneous coordinate. Okay, so inhomogeneous coordinate. So we have to convert this inhomogeneous into homogeneous coordinate in case of projective space. I said R is real space, P is projective space. Projective space in the sense we can represent any point or line in a camera angle. Okay, so this 2D point in homogeneous condition, in homogeneous form, we can represent it as x bar equal to x bar comma y bar comma w bar. Additionally, I am adding one more parameter w bar in order to represent the data in projective space. Okay, so projective space, right? So using this point, using a homogeneous coordinate, we can represent the point in infinity using projective geometry. Okay, let us see how to convert the homogeneous, that is inhomogeneous. This 2D point is known as inhomogeneous. Inhomogeneous to homogeneous. Okay, first let us start with the 2D point. Let us start with the 2D point x equal to x comma y, and we have to turn into x bar is having three parameters, right? So x comma y comma 1, which means this x comma 1 is equivalent to x comma y comma 1. This x comma y is the point in real space, x comma y comma 1 is in the real space, so sorry, projective space. So we can multiply some values also. This 2 comma 2 is equivalent to x comma y comma 1, because we are multiplying the value 2 with all the parameters, right? So here we can represent x comma y to x comma y comma w. So this is known as inhomogeneous to homogeneous. Similarly, we can write homogeneous to inhomogeneous. If you are representing a point in a real space, projective space, if you want to convert into real space, means we have to convert the 3 points x comma y comma w to x comma y, right? So we know homogeneous point is x bar y bar w, right? So we have to convert to 2 parameters, that is x comma y. So we have to convert to x comma y, which is nothing but dividing the value, dividing the third parameter gives two values, right? So x bar, y bar, w bar, three values has been converted to only two values. So what we are doing in the previous case, we are additionally adding one parameter of value 1. In this case, three parameters can be converted to two parameters by dividing the third parameter with first and second parameter. So assume if w bar is equal to 0, then all the denominator would become 0. If x and y is also 0 means we will have 0 by 0. Then the w bar equal to 0 means we can say this point is at infinity. We can't represent any point in infinity in real space, right? So if the third parameter is 0, this in this projective space we can represent the point in infinity, but in real space if we are writing the point in a paper we can't represent the point in infinity, right? So the point at infinity cannot be used in 2D space. Point at infinity is not possible, is not possible in 2D space. Remaining all the points can be converted. If you are writing 2 comma 3 means it can be converted to 2 comma 3 comma 1. And this is real space, this is projective space. Again, if I want to convert into real space means what I'll do, 2 by 1 comma 3 by 1, it will become a real space. So if I am representing point at infinity in projective space means it will become 2 by 0, 3 by 0. Is projective space it is possible, but in case of real space it is not possible. So what we are concluding is all the projective points belong to real points, belong to real space points except 0 comma 0 comma 0. So we can't represent a point at infinity in 2D space. So we are representing all the projective space is equivalent to real space except the point 0 comma 0 comma 0. That is what given in the slide. So a 2D point can be represented as x equal to x comma y, which is equivalent to real space, and we are representing it in a matrix. So it can be converted into homogeneous coordinates by converting into three parameters, which is equivalent to projective space. All the projective space are equivalent to real space except 0 comma 0 comma 0, and we know that if I want to, so this three parameters we have already seen. If I want to convert the homogeneous vector into inhomogeneous vector, we have to divide the value with the last element w bar. Okay, so x comma y comma 1 is also known as a augmented vector. If w equal to 0 means this point is at infinity, or we can say it as a ideal point, and we don't have any equivalent inhomogeneous representation. So I hope you are clear with the 2D points. Next we'll see 2D line. So in 2D line, a simple line equation can be represented. Simple line equation you might have studied in lower standards can be represented by the equation ax plus by plus c equal to 0. Let us say example 2x plus 3y plus 6 or 3y minus 6 equal to 0, which is nothing but a line in 2D space, right? Plus 6 or minus 6, whatever may be. So we know the line in 2D, then we have to convert into homogeneous. This is inhomogeneous. We have to convert into homogeneous line vector. Homogeneous line vector can be represented as L bar equal to A comma B comma C. Ax plus B, Y plus C can be represented as A comma B comma C. So here, as per the example we have taken, we can represent 2 comma 3 comma minus 6. If we have taken plus 6 means it will be plus 6. Right? So this is nothing but a homogeneous line. Homogeneous line, which is a different way to store the line. One form of storing the line. Like what we have seen is in a previous points, right? So we know homogeneous way as well as inhomogeneous way. Similarly we are representing it, right? Normal 2D is represented as inhomogeneous. Converting to the projective space it will become a homogeneous. And we know that a homogeneous point, we know that homogeneous point can be represented as x bar equal to x comma y comma 1, right? With three parameters we can represent. So now we know homogeneous line vector can be represented as L bar equal to a comma b comma c, and homogeneous point can be represented as x comma y comma 1. If we want or check a point that is lies on the line, so we know point and this is the line. A point may also lie in a line, right? So in order to check if a point given point lies in a line or not, then we have to use this equation to check. Sorry, homogeneous point into homogeneous line equal to 0. If this condition satisfied, then I can say the point is on the line. If the condition is satisfied means we can conclude the point is on the line. So let us take a simple line equation, x plus y minus 5 equal to 0, and a point to x equal to 2 comma 3. So in homogeneous way we can represent it as L bar equal to 1 comma 1 comma minus 5. Here x bar equal to we can say 2 comma 3 comma 1. As per the equation, x bar into L bar equal to 2 into 1. I am just multiplying it. 2 into 1 plus 3 into 1 plus minus 5 into 1, which is nothing but 2 plus 3 minus 5, which is equal to 0. So we can conclude the point 2 comma 3 is lies on the line. If this is not equal to 0 means the point and line are separate, right? So in order to normalize this we can add n bar. Okay, so let us see. The 2D line can be represented as a homogeneous coordinate as L bar equal to a comma b comma c. The corresponding equation is x bar into L bar equal to 0. If this condition is satisfied means we can conclude the point is at line. So the line equation is given here. So if to check if the point is available, lies in the line or not, we can check using this equation. And see here, the perpendicular line has been drawn. The distance between the origin and the line is d, and the perpendicular distance above the line is represented as n cap, and the angle between the line is represented as origin to the line is represented as theta. So instead of a comma b comma c, we can represent n bar x comma n bar y comma d if n is equivalent to 1. So we know that n cap is the this distance and theta is the distance between origin to the line. And we can say if the line is at infinity, in this condition 0 comma 0 comma 1. And this equation is used to represent the intersection of two lines. So here we have seen the point lies in the line or not. So I want to see the intersection of two lines are there which may be parallel, which may not intersect. If they are intersecting at each other means we have to use the represent, we have to represent x bar equal to L1 bar into L2 bar. Similarly, the line joining 2 points, so every line will have 2 points, right? X comma y and x comma y. The line joining 2 points can be represented by using L bar equal to x1 bar into x2 bar. Then we are going to see about 2D conics. So every conics is a form of circle, right? So we know the conics. Sorry. So this is the conic shape. So the circle, every circle will become a conic shape. So I'm going to write the circle equation. So this equation represents circle with radius 1. This line can also be represented as x square plus y square minus 1 equal to 0. And we also know homogeneous point x bar is equal to x comma y comma 1. This can be represented in matrix x, y and 1. And we are having a matrix called Q with the following values: 1 0 0, 0 1 0, 0 0, minus 1. Okay, so we have one more equation, x bar transpose into qx bar, so equal to 0. This is the equation given here. Okay, this is the equation given here. I'm going to write the same. And what I have said is what is x bar and what is q. X bar is nothing but x comma y comma 1, 2D point represents the homogeneous condition, and the q matrix a separate value is given, and the equation given is x bar transpose into q into x bar, right? So what I'm going to do is I'm going to substitute these values in this equation. So x bar transport would become xy1, and we know the Q matrix 1 0 0 0 1 0 0 0 minus 1, and x bar will be x y 1. First I'm going to multiply this. If q x bar is multiplied means x y and minus 1, right? So x y minus 1 is the value, and I'm going to substitute this in x transpose into q into x equal to 0. This is the equation. What we have identified is q x bar, and x transpose is x y 1. So x y 1 into x y minus 1. On multiplying this matrix, we'll get x square plus y square minus 1. So we know the equation x bar transpose into q dot x equal to 0. What we have identified is x square plus y square minus 1, 1, and I can equate this to 0, which means x square plus y square equal to 1. What I am concluding is the circle can become the 2D coordinates using the equation x bar transpose into q into x bar equal to 0. That is what represented in this equation. So far we have seen 2D points, 2D lines, and 2D conics. These are the geometric primitives of 2D representation only. Next we will see about 3D representation. Thank you.